everybody. First, thank you to Credit Suisse for allowing us to host it over here. My name is Chandra, and it's great to meet you. So we're going to talk about GS collections and Java 8. First, with a show of hands, how many of you are already using Java 8 in production systems? It's a decent turnout, right? How many of you know the features available in Java 8? At least towards collections, right? Java 7. And I'm going to directly jump to Java 5. Sorry.
I heard it's end of life.
Java 5. Good. Great to hear. How many of you have heard of GS collections? Great. Great. With that, we're going to get started. I'm just going to start with what we're going to present today. And we're first going to cover a little bit about what GS collections, why GS collections, what prompted us to come up with GS collections. And then we'll go into some more topics of how we sort of complement and supplement Java 8 with the features that are offered in GS collections. So first, GS collections is a collections framework library that was created a while back, 2004. And some of the original creators are here. And it was developed in-house as an internal application, and then it was finally outsourced, and it is available on open source, and it's available on GitHub. We will share the links towards the end of the presentation as well. So it's hosted on GitHub within Apache 2.1, so you can tell the links right there. In addition to having a collections framework, which the reason for the collection framework itself was the fact that we were noticing patterns in how we use our collection libraries, the Java collection libraries. And we would look at a repeated set of patterns that we were using. We decided to sort of extract these patterns and convert them into independent anonymous classes or blocks that we could reuse. Right? Also, if you ever take a look at most of the Java API prior to Java 8, you will notice that you actually have to externalize yourself from the actual collection in order to perform some actions. So, simple example, you have a list. What do you do with the list? You want to iterate over a list. You don't use the list directly. You actually create a for loop or some kind of iteration pattern and then go through the list. Now, this deviates you from the actual thought process of using the list. You actually have to use constructs that are not inherent to the list itself. So GS collections was originally developed as a means of bringing about some sort of fluency to the list itself. Right. In order to learn GS collections, sorry, can you hear me better now? So in order to use GS collections, we were faced with our own challenges. How do we train people to use GS collections? So we also developed what is called a kata. How many of you know the term kata? Great. So for those who aren't familiar, kata is essentially a training exercise where through repeated performance of the same activity, you learn and develop new skills. So we created a GS collections kata, and it's been quite successful. We've used it to train about 1,500 of our own GS developers to use GS collections. It too is open source and available on GitHub. We'll be sharing the links towards the end of the presentation. So, why did we come up with GS collections? So, how many of you are familiar with Chandra? Great option. Back in '97, Chandra had described some programming patterns and used Motlin as a basis for describing the patterns. If you look at the APIs on your, I guess, to my right, you'll notice that there are a few patterns that say do, perform operations iteratively, select, filtration criteria, reject, collect, which will transform, detect, etc. Right? Most of these APIs back then were developed because there was no easy IDE base. You couldn't hit control space and get code completions. So what would you do? You would create APIs that were easy to memorize, just like our Swiss, right? You would create words that were easy to remember, and you would figure out how to use the API, right? So great, that was the past. That was back in '97, and I guess I am guilty of speaking in with nostalgia because I'm a small talk developer myself. And how many of you know small talk? No, so great. So Smalltalk had these APIs, and it was very easy to use. You didn't have to memorize much. You just thought about what operation to perform, and you knew what method to call. There was no code completion back then, so it sort of helped to have it easy to remember. Great. Fast forward to 2007, came back to another pattern. It's called the implementation pattern, and this time the usage was based on Java. As you can notice on your right, you have the actual object that you use in the collection framework. However, all the beautiful patterns that you had to just memorize and use are gone. They're replaced with instant code completions in order to help you out. But it's not very easy and intuitive for you at the beginning, right? So that is what we like to define as paradise lost. This was a time in our life when we had rich APIs which you can memorize and use. Fast forward 10 years, and you don't have it. So it was a loss, right? So the intended purpose of GS collection was to go out and create, or recreate rather, some sort of paradise. So that paradise was found back. How did we achieve this? This slide is a bit more busy, but if you focus, you notice that we have patterns in Smalltalk, how they were used, compared to what the classic patterns in Java look like, and how we achieve similar results using GS collections. Now, if you notice, you have detect, which is a pattern in order to find out, which is a filtration kind of pattern. And you notice that we use a predicate, similar to how it was used in Smalltalk, and we extract whatever we need. Likewise, the other APIs for select, reject, we can do any satisfy, all satisfy, collect, inject, as the Smalltalk. Equivalence in Java can be achieved, but they were more verbose, and they followed somewhat of boilerplate text that you have to write in order to achieve them. Right? So, going deeper into GS collections, we have GS collections implicitly is what we call eager collections. You could essentially go into GS collections, access your collections, and perform filtration or transformation operations on those. Some of the examples we just have here are GS collections, detect, lazy, etc. So, I'm sorry, I'll jump over into it. We support both eager patterns as well as lazy patterns in GS collections. Some of the patterns that we declare over here are lazy, as you can see. List as lazy would return as a lazy iterative. If we were to get it eager, we would actually just do list.detect, which we saw in the prior example. In this slide. Great. So here we actually compare both our APIs with both eager as well as lazy operations. As you can notice, we have eager GS collections which show detection, selection, rejection patterns, and then equivalence in Java 8, which can be achieved using the stream. How many of you have used the stream? So if you notice the Java 8 streams, you will see that we have, in order to achieve the predicate of just filtering, let's take the first example, where we are detecting any element that is of greater than 50 size. What do we do in eager GS collections? We actually just detect and we have a predicate in order to fill out the results. In Java 8, in order to do so, we actually have this meet and one concept, where we actually have a meet of predicate E greater than 50, but in order to achieve that, we also need to sandwich it with some text to stream and text at the bottom to select it later. So this is GS collections. And is that right?
Okay, so you've seen a few examples, and I know from the discussion before that you guys are thinking about functional patterns. I heard talk about Scala, and I hope you can see from some of these patterns some of the style that we think about when we're coding. So we've had a chance to use Java 8 for like a year now. The impression that we get is it's a great framework. Streams are a great addition. They provide all these iteration patterns, which, well, they provide some iteration patterns, some of the ones that we saw all the way going back to Smalltalk. They're lazy by default, as we just saw, which is an interesting design choice. They could have had eager as well. But lazy is very frequently what you do want. We'll see some code examples later, but streams support both eager and serial and parallel evaluation, and it's through almost identical API, which is also very nice in terms of the learning curve. There's some support for primitives, which we'll see in 3 primitive streams, int, long, and double, and they're very extensible through collectors, and I have a bunch of code examples, so we'll take a close look at collectors. But if you haven't seen the pattern yet, like the 7 or so patterns that we've been going through, you can usually achieve what you want by building up something bigger through collectors. But even with all that said, to us, you know, the ones who have been working on JS collections and looking at the competition and seeing what's available, Java 8 streams really feels like just the tip of an iceberg, and there's a whole bunch more that's not there in streams. What they've achieved in a little bit of code, the addition of the streams library, is remarkable, but it's really just the tip of the iceberg. So, what is in this iceberg? What doesn't streams have that we want? Direct eager iteration patterns, as Chandra was talking about. Covariant return types on collection protocols. So, covariant return types just means when you return something more specific from a subclass. So, for example, if I'm filtering a list, I know I'm getting back a subset of it. I know it still might have duplicates. I know it's still in order. So I want back a list. With streams, you always just get back the same text. You get a string no matter what you're doing. Like, continuing the example, if I filter a set, after filtering, it still is probably unordered, and it has only unique elements. So that's what I mean by covariant return types. There's no new collection types in Java 8. All these behaviors are through streams, but the streams you get through list, sets, and maps. There's no new types. For extra types, you still have to use third-party libraries like ours or Lava. And in there we have multi-maps, bags, which are also called multi-sets, bi-maps, and any other containers. There's no real optimizations to the containers that are there. There's no API, but the containers themselves there's minor modifications. For the most part, they're untouched. And there's really big performance problems in Hashset and Hashmap, which we'll talk about later. There are primitive streams, but not primitive containers, and that matters a lot for memory. And there's no immutable containers. So if you are one of the folks who care about functional style, and you still don't have immutable containers, you have streams which don't have any mutating API, for the most part, right? Only collections have mutating API. Streams you read, but it might be on something mutating under you, or it might not. Okay, on this slide I have a bunch of statistics. The most important one is at the end, the lines of code, but I'll touch on a few of these. So, the second one, functional interfaces. In JS collections, there's a whole bunch of functional interfaces. In Java 8, there's only a few. The functional interfaces are the ones that have a single abstract method type, the ones that you can use the Java 8 compiler to compile a lambda into them. So they're like function and predicate and consumer. They also had to create forms that take 2 arguments, like by function, and 3 arguments in some cases. But you know, they can't do it forever because it's not abstracted over parity. You have to write a new type each time. So they limited it as much as they could. It explodes with primitives, but that's why they only did int, long, and double. If you really want to do it all, before you have anything like value types in the language, you wind up having a ton of interfaces. And so we just do that. We have a lot of interfaces. The actual number of containers is lower. I mean, I mentioned that, but it explodes in terms of mutable and immutable. List, set, and map to start with, but then bags, multi-maps, etc. There are no primitive container interfaces in Java 8. I mentioned that. There's only the 3 streams, but not containers like int, list, int, set, just in stream. The reason our number is so high is because when it comes to maps, we want to allow a primitive or object as the key, and a primitive or object as the value, and there's 8 primitives each, so it multiplies out, and we have a huge number of maps. The other point about primitives is that we want to achieve some parity between the API available in primitive collections and object collections. And since they came along later, we don't have complete parity there, so we have fewer methods than are available in streams with more types, so there's a lot of methods there overall. And lines of code, I don't like it as a metric, but it's all we've really got to compare size. The streams API, as a delta, it added about 15,000 lines to the core libraries. And like I said before, it's a remarkable amount that they've been able to achieve in 15,000 lines. All of these evaluation, these iteration patterns that we haven't had before are there in just 15,000 lines. But like I said, it's just the tip of the iceberg, and that's why JS Collections is 14,000 lines of handwritten code. And that includes the templates. I count the templates as handwritten that generate the primitive collections. After exploiting out for all the primitive key and value types and lists and sets and bags and stacks, we wind up with over 1 million lines of generated code for the primitives. So it's quite a large library. And I think it's important to think about what features that are in there ought to be in Java itself. Because Java 8, I feel like with streams, they added enough into the library that you could use lambdas and get familiar with them, and enough that it justifies the existence of like changing the compiler, changing the virtual machine, adding new bytecodes. But there's a whole bunch more they could do in the collections themselves. Now, JS Collections, like I said, it's a big library. It's so big that I'm sure we'll never get to the point where all of it is in Java itself. And there's things that are in there that are experiments, so it's not even appropriate to say all of it will get in. But other libraries that are open source have influenced and gradually been pulled into the JDK itself. So that's what I want people to kind of think about. Which of these features that you see are important enough that they belong in there, and which will interact well with the features that are already there? At this point, Java 9, the feature set is already set, and it's actually mostly internal to the JVM. It's like a refactoring and modularization of this. Java 10 is the first chance to have additional library changes at the scale of what we've seen in Java 8. So I'm thinking that far ahead. Like Java 10, what features should it have that are sort of like a collections 2.0? We've talked with some of the Oracle engineers, and they consider streams like collections 1.0. It's an addition, sorry, 1.5. It's an addition to the collections framework. It's not a replacement. It's not a 2.0. And there's room for that in the future through a JSR. Okay, I'm going to get into some of the specific patterns that I said were not there. We saw select and collect, which are like filter and map, and a few others. But these are patterns which aren't there on streams themselves. You might be familiar with some of these patterns from other languages. I think these are the same names for the most part that Scala has. So those of you who are talking about Scala, you're probably familiar with these patterns. So let's see, how do you do that in Java 8 today? And how do you do it with JS Collections? I mentioned collectors. Collectors is going to be the way that we achieve most of these things. They are the extension point. They are a form of static utility. We'll see the code examples. Actually, let me just jump ahead and show one to make this more clear. This is joining versus make string. This is how you would transform a list of objects into a single comma-separated string. For JS Collections, at the bottom, we just take a list of things and call make string. And everything else is done internally. To do this with streams, you first, of course, have to opt into the stream by calling .stream. First, map each item to a string, which seems redundant. That could have been done in the collector itself. But the most important thing here is, if it's not a method on stream itself, it's going to usually be something you achieve through collector by calling collect and passing in the collector. Collector is static utility, as I mentioned. That means you don't write a new collector. You instantiate it through a factory method like this one, join. All right, so getting back to utility, whenever we've worked with utility APIs in the past, and we do have utility APIs in JS Collections, we wind up talking about the futility of utility. It has pros and cons, but more cons. The main benefit is that it's very easy to write an extensible API, just add new things, new static methods. It's easy for us as library developers to add new static methods because it doesn't break backwards compatibility, it doesn't break source compatibility. You can always just do it in any release. But it's hard to discover. Your IDE won't help you with autocomplete because it's on some class that you're not working with. You want to do like list dot and see the behaviors pop up in your IDE that you have as a choice. You have to remember now that some new API is on stream, and if it's not there, call collect and then look around on collectors. And you can read about it. It's, like anything, it's a learning curve, so you can learn it here. But for the most part, we would prefer regular API over utility. There's also some points here about readability that's subjective, but in my opinion, it's usually easier to read regular API than static utility, and hopefully these code examples will show that. So we're doing one through joining and make string. Here's another similar example when you want to sum some attributes. So we have a list of employees or a collection of employees, and we want to sum their salaries. All of these examples start with stream and immediately terminate with collect and pass in a collector. In this case, we configure the summing collector by passing in a function. In this case, we're instantiating the function using a method reference. So we're just referring to this method getSalary, which returns an int, I guess. And I've bolded the return type here. It's probably a mistake for this summing int API to return an int, because it's very easy to overflow. It probably ought to have been a long. In JS collections, this pattern is just a named pattern, sum of int. It's right on all of the collections. So hopefully the readability points I made before are clear, and also the return type there is long. It's interesting, I think that the return type being an int, even though it's a mistake, I feel like they can't fix it, because they never can fix things like this in the JDK. Once it's shipped, backwards compatibility is king, and it's probably there to stay. It also ends up affecting other APIs, which we'll see later. All right, let's see how this stuff stacks and gets a little bit more complicated. This one is group by. We want to take that list of employees and group them by their department. So afterwards, we'll have a structure where we can query, like we'll get by department, and we'll get all the employees in that department. Here, the collector that we pass in is actually similar to what we passed in before. It's just, it's grouping by now, but it still just gets a function which says how we're grouping. It's how we create the key. And the return type is a map of departments to a list of employees. It's like a multi-map if you're familiar with multi-maps. And JS Collections does return a multi-map. But one of the interesting things here is that the return type doesn't vary. I talked about covariant return types before. It doesn't really matter here if employees is a list or a set. No matter what, after calling stream and using the grouping by collector, I'll get back a map of departments to lists of employees. So to me that feels weird because lists are ordered. It implies that the ordering is meaningful. It also doesn't tell you anything about the duplicates. If I started with a hash set, I would wind up with these lists that have unique elements and have no meaningful order. So I want back a map of departments to sets of employees in that case. And that's not really possible to achieve through this sort of API. You need API on your interfaces with covariant return types. So that's what we have with JS Collections. In this case, if all I know is that it's a rich iterable, which is our top type of the whole hierarchy, I'll get back a multi-map from group by. But if employees is a list, I'll get back a list multi-map, and if it's a set, I'll get back a set multi-map. And on that, when I call get, I'll get the right type back, either a list or a set. Or back. We'll talk about that type. By the way, feel free to interrupt. There's a lot of code examples, so let me pause here while I'm thinking about it. Are there any questions about the code examples? Yes?
So just going back to your lines of code slides, the fact that I will get back a type, it's all code gen, like there are code gen versions for each possibility there?
We use code generation for primitive types. So these code examples that I'm showing are all the object types. Like a list of employees is a regular object list, generified. But we will generate int list, long list, double list, etc. I think I have some examples of that late in the presentation, but so far this is all the object API. And it's all handwritten, this stuff. Yes?
So the return type is multi-map, department of employees. You figure that out based on the fact that employees is that's the type, employee type, and you're giving it the group by and get department from department type, and that's how you're able to construct multi-map?
Yes, that's right. So group by, as it's defined at the top, returns a multi-map, and multi-map has a ton of subclasses. It has mutable and immutable multi-maps, and it has ones where the values are represented by lists, sets, and bags. And so if employee, these are all our own interfaces, but they all kind of interoperate. Like our mutable list extends list. So if employees is a mutable list, you will get back a mutable list multi-map. And it's like a map in that it has methods like get and put, but they're different because get returns your, in this case, mutable list of employees instead of a single one. Do you have any questions?
When you get back, if you ask a map for a key that doesn't exist, and when you get back, if you ask a multi-map for a key that doesn't exist.
Great question. So what do I get back if I query a multi-map by calling get for a key that's not there? In a regular map, you know you would get back null. In a multi-map, you would get back an empty collection. So it's just a nice way of avoiding null pointer exceptions. And that's one of the things that multi-maps give you in any implementation. Guavas are just like that too. So if you, when you call put, you don't worry about putting in the initial empty collection. It does it for you. And when you remove the last one, it takes out the key and the empty collection. Yes?
So did you consider compatibility with, say, Google collections, or just because of best practices they converge sort of? Like, for example, Google implementation of multi-map has the same behavior, basically. Returns empty collection of values if it does not exist.
Right, so compatibility with Guava. Part of it is history and part of it is choice. So, like Chandra mentioned, the library was closed source for years before we open sourced it. So it's actually older than Guava, even though Guava's, it was open sourced earlier and it's much more known. The APIs are similar partially because they're both just, you arrive at the same conclusions as you design it. But, we definitely took inspiration from some of the aspects of it. Now there's other things that we have that are not in Guava's multi-map, so there's differences. And the main one is that these iteration patterns we're talking about are on the multi-map. So you could call multi-map.select, for example, and filter by keys or values or both, depending on the predicate you're passing. So a lot more iteration patterns on them, and then the other difference is that Guava considers itself a supplement to the library. It doesn't attempt to replace it. So they won't do things like have a replacement set or map. So that means in Guava, where they do have a set multi-map, it'll be backed by a hash set, a hash map rather, and the values will all be hash sets. And I'll talk about the performance problems of that later, but we've replaced both hash map and hash set, and our multi-maps are built on top of that. But if you're familiar with Guava or you're familiar with the Scala collections library, all of this stuff should be familiar, and it just kind of brings it to Java. Streams is doing that, by the way. I mean, it's bringing these familiar concepts to Java developers, but it's like a little bit of it. It's just the Streams API. Okay, you can see we're building up larger and larger collectors, doing more and more complicated patterns. So this is the first one where you see collector delegate to another collector. It's an aggregation pattern. What we're actually doing here is taking our list of employees and we're aggregating their salaries by department. So we'll have in the end a map structure where for each department you can query for the sum of salaries. We start with a grouping by collector again. We're grouping by the same function to get the department. And now it's an overload of grouping by that takes a second argument, another collector. And this is another collector we actually saw before, the one that sums the salaries. And so altogether, like now your API feels like it's not the streams API, it's the collectors API. It's this huge collector and it gives you back a map of department to int. And I mentioned this before, int, right? It should be a long, because it's very easy to overflow. So this is the second place that API serves, is returning int. This pattern of math aggregation, where it's just a sum, is common enough that we added it right onto our types, and we called it sum by int, or sum by long, or whatever you're summing by. And it is a more complicated pattern, so it's still going to be more complicated than let's say just doing a filter. In this case, we have to take two functions. It's still the same two, but those are your only arguments. And it gives you back a special type, object long map. So this is one where internally, the keys are departments, and the values are primitive longs, not long wrapper objects. And so even though they're wider types, it's still going to be more memory efficient than a hash map, holding departments and integers. This is the last example, and it's the last one where the return type is really interesting. This is the partition pattern. It's like doing a filter and a filter not, or select and reject at the same time. In this case, we take a list of students, and we partition them based on whether their grade is passing or failing. So in this case, the collector is straightforward, I'm not going to go through it. The iteration pattern for both is straightforward, but it's another case where the covariant return type, or I would want a covariant return type, and with streams I don't get it. Same thing, I get back a map of Boolean, which is kind of weird, because there's only two keys, true and false, and for each one I'll get the list of passing or failing students, and it doesn't matter if students is a list or a set. I always get back a list. So for JS collections, we kind of just wanted to return a pair, like our own type, a pair of lists. But you can't do that in Java because the generics have this limitation that they have to be invariant. So if you want covariant return types, you kind of have to just define your own type, which is what we did. So we have our custom type partition, which has two methods to get selected and get rejected items, and a ton of covariant return covariant subclasses that we use for overrides of partition. So in this case, I've got a list, I get back a partition list. It gets more specific. I could have a partition mutable list to show that I was splitting the mutable list. How do they stack up? So this is kind of an interesting side note. In the last test for partitions, we wanted to take a deeper dive into streams, and what we did is we just put a breakpoint inside the lambda itself, the thing that gets the grade for the students while we're partitioning the students, and just see how we get there. What's the code path? And on the left side we have streams, on the right side we have JS collections, and obviously the stack depth is different. But reading up from the bottom, because that's the order of the call stack here, most of the API from calling partition on streams is actually going through just generic stream code and has nothing to do with partitions. And it gets back to code sharing and code reuse, but no covariant return types. It's basically the same implementation for anything that calls collect. And you have to iterate all the way until you get up to the point where it's executing the lambda that's built out of the collector to see what's happening differently. So up from the bottom, we see collect first. They all had collect, obviously. And then internally, we have evaluate and evaluate sequential next. So we'll take a look at parallel later, but the beginning is just saying we're doing serial evaluation. Then the next is wrap and copy into for each remaining, for each remaining. All of that is the same for any serial pattern. And then we get accept, so that's a method that the lambdas have. And then finally, you can see there the actual lambda being called. And it has embedded in our partitioning block. So all of the bottom, which is like 10 stack frames, is common to all the collect patterns, which is great code reuse. But if you wanted to step through it, it's a bit hard to understand what's going on. With JS collections, you step into partition and you're immediately in partition code because it's just written, like every pattern is kind of handwritten to be optimized for that specific pattern. So that's why JS collections is a lot more code, but it's a bit easier to read in my opinion. After partition, we're right into, it's partitioning an abstract list that we share code between different lists. And then it's into some static utility we use to iterate through the internal array, but you're immediately in partitioning code. So if you actually step through it, it's a bit easier to read. I assume there's performance differences that are minor between them because of this code reuse. You get into megamorphic call sites and stuff like that, if you know about that. There's more likely to be megamorphic problems in the code sharing version on the left. Okay. So that's it for the API stuff. I'm going to hand it back to Chandra to talk about fluency.
Thanks, Great. So we're going to start talking about fluency by taking an example. We're going to use the standard example that's out there on the Oracle site. It's basically an anagram example where, given a word, you try to find out different possible combinations of what that word can come out as. And one of the examples is alerts, for example. That's what we show out here. And how we can list out all possible anagrams of a given word. The first we're going to do is we're going to try this with regular Java 8 syntax, and then we will walk through how it appears in TS collections. So the anagram tutorial in Java, I'll explain it step by step. The first thing we do is words, get words returns us a collection. Obviously, in Java, we cannot directly operate upon the collection. We need to stream, and that's what we do first, to get a stream of the words. From the stream, we actually collect, and as Greg mentioned earlier, we use the collectors, grouping by, in order to get a map of collections, and we return a map of alphagram to a list of strings. This would allow us to get words based upon an alphagram, and we can actually list out two kinds of alphagrams. Great. Once we get the list out of it, we need to extract from that map, which we will actually show. So at the stream, we actually collect and we get a map of an epigram to a list of strings from which we extract values, which would give us the list of strings to process. Since it's again a list, we need to stream it. We stream that list. This is a double stream pattern we get. And once we get a stream of the strings that we are trying to operate upon, we filter them for a given size threshold. So the anagram example, if you look at it, we actually have a, we don't have a directory here. I don't think we connected to the internet. Alright, so the anagrams, basically, there's a size threshold of the anagrams that we would like to display, and that is what we're checking on the size threshold. And once we get the size, we sort the anagrams according to their, we sort them alphabetically in the reverse order. And this returns another, this gives us another list. This list is a sorted list of all the anagrams that we filtered out, from which we actually map each of those to a different list containing both the size and the element. If you notice the example, we have 11, which is the size, and the elements in there, right? So that's what we are creating another list for, and then running for each on that in order to print out each of those strings. The Java version has two streams that the Java version has two streams that we actually have to process through in order to get to the collection itself. So we look at how it looks like in the GS collections equivalent. GS collections, we again have to do the get words in order to get the list. But now, we, as I mentioned earlier, we can simply do a group by. The group by would give us a mutable list multiplier, which is what we can process because it is a list, a mutable list, and it provides us a multi-map to do the group by. From this multi-map, we get a multi-value stream, and as Craig was mentioning about invariants, this is the only place where GS collections sort of shares its lack of variances with Java, where you have to return a rich iterable type. You get a rich iterable out of this, and that rich iterable you would select and actually process to filter out any words that do not match the size threshold. Once you have a size threshold, you sort it using the rich iterable size, you reverse it. Reversal, GS collections has this pattern where anything that starts with an as, we typically try to provide a wrapper, and therefore this returns what is the lazy iterable. We then collect from this list, process it, and produce a string that has the size as well as the elements, and then we print them. Any questions on how the GS collections operations work?
What's the type on the multi-value queue call?
It's a rich iterable of rich iterables.
Oh, right, okay, there it is.
So this is another example of a parallel lazy iteration. As you will notice, the top example is Java, and the lower example is GS collections. In the Java example, we have a stream of addresses produced from the parallel stream. Java has this API stream as well as the parallel stream. In the parallel stream API, which Java provides, we actually come up with a stream which is very similar to what a serial stream would produce. But the onus is on us as developers to understand that this is a parallel stream. There is no difference in the API to the return. However, in GS collections, we actually understand with the as parallel method that this is a parallel API call, and therefore we return a parallel list iterable rather than a list iterable. Therefore, although the API itself, we continue to access using the same kind of collections, we don't have to necessarily remember that we are parallel, whereas in the Java API, we do have to remember that there is a parallel call, and we have to act accordingly. There's more on this that Craig has already written extensively about in the intro presentation, and it's at Java Streams. The link is also supplied at the end of the presentation. Right?
So can I ask a question on that? Why is that a good thing for the design? In this case, knowing that it's a parallel, like what's your take on why it's a good thing? Rather than exposed in code.
So if you are performing a parallel operation and you actually were to care about the sequence of elements coming in, the onus is on you to actually know that the functions you're calling are parallel. versus in GS collections that is already taken care of.
Another thing is that when you have a parallel stream and you pass in a function, for example, in this case, it's person get address. It's probably a stateless function, something that just gets the person's address. It's just going to call getter. But occasionally you'll pass in something stateful, and now it's up to you to remember this thing is going to be called in parallel. It's one function, but we call for multiple threads, so it better be thread safe or totally immutable, state free. So I prefer having it in the API reminding me it's parallel, and then as long as I have custom return types, might as well preserve the information that's a list or a set that I started with, for the same reasons we talked about covariance before. Another question?
So regarding thread safety, you go back to the group by and all the other patterns that we talked about. Does the GS collection actually support thread safety with respect to assuming the collection may be concurrent or non-concurrent on what it's operating upon? So do you get like a group by fail-safe, or do you get like another group by option if you want to do it? Because there's very much possibility by the time you do the streaming and loop out. So the first question is, how does the collection API perform? Does it just give you the filtered values with respect to other data missing, or does it just give an exception?
Okay, well, there's a few questions there. Just to emphasize, in this example, words we're assuming is a regular serial list. We haven't called as parallel. So everything that follows is an eager return type in this example. If after get words you also wrote as parallel, like on this slide, and you passed in your executor and your batch size, the return types would all be different. So the very first thing we do afterwards is called group by. It would be on a different type, a parallel list interval, and it would return back. Well, it depends. Like some things are more lazy than others. Group by has to evaluate, and the type that it happens to group into. It also depends on if it's a list or a set you're starting with. So it'll be a multi-map backed by concurrent map, first of all, and then depending on what the type is, the values will be synchronized or handled in a thread safe way. That depends on the type. So that's really the theme here. For all these methods are written several times for the type that they're on. Does that answer?
Do you recommend using the actual object to be immutable itself that you're trying to do filtration operation on?
So do we recommend immutable collections first? Yeah, there's pros and cons. If you're really not changing it, the immutable collections are a great choice because they're always more memory efficient. They're always, if it's a list, it's trimmed. If it's a set, like it's just after resize, for example. They're always no bigger than the immutable collection, so that's nice. And they communicate that they won't change, and they're thread safe. The biggest downside is the interop is a little bit trickier than mutable collections, because like our mutable list just directly extends the list. On our immutable list, we don't want the method add and remove public. That's one of the biggest differences between us and Guava. Guava's immutable list is a list. It looks mutable, and it throws at runtime. But we have views that let you interoperate, and as long as you don't call the mutating methods on the views, you're okay. So besides that, it's kind of the usual pros and cons between mutable and immutable collection. Oh, one other thing I wanted to point out about this presentation is linked. In this, we really only have time to talk about API. The whole thing here is API. But that presentation is really about performance. And I have a whole hour-long talk where I dive into performance of Java H streams in parallel, GS collections, parallel streams, and Scala's parallel collections as well, because they have a similar API. You can guess what my message would be, because I'm biased, but Java H streams have some performance problems in there. Okay, next topic is on memory efficiency. So I mentioned earlier that maps and Hashmap and Hashset have a performance problem. They have a few, but the main one is their memory use. These charts show on the y-axis we have the number of megabytes used, on the x-axis we have the size of the map, and I'm showing the JDK hash map in orange, our JS Collections unified map in blue, and I also showed Trove here because it has an interesting growth strategy. One second. Our map and the built-in map have this growth strategy where any new collisions and go into a bucket that's basically a linked list. So you have this gentle slope as you're getting more collisions here. And then you get to a point where you decide to do a resize and it doubles the backing array and you get this sharper slope. So that shape here and our shape is the same, but just off by a factor of 2. And then Troves, it uses open addressing. There are no linked lists for collisions. The collisions go right into the array in a different slot using some probing algorithm. And so you get this characteristic flat line of open addressing, and then a periodic complete doubling. Sorry, before I go on to this question.
What are the keys and values?
So I think in this we're just using strings or something, but we actually were careful not to measure the size of the objects that are being contained. So we pre-initialized all of them, checked the memory usage, and then put them from an array into the collection. So this is just the overhead of the collection. Right, so when I say 40 megabytes, for example, that's just the collection, not the strings in it. Okay, so the main problem with Hashmap is that it's backed by a table of entry objects. The entry object is really interesting. It holds the key and the value, of course. It also holds a next pointer. That's how collisions are handled. It's a linked list of collisions. It also caches the hash code, which is a really interesting time memory trade-off. Because, of course, it uses memory to cache, but every once in a while, as you grow a hash map, it has to double in size. So when you cache, this is pretty much the most expensive thing you can do with a hash map. So if you've cached the hash code, it's a lot faster. Of course, you don't want this if you know it's immutable. If you know you're growing it and you're never going to resize it, no point in speeding up the resize. It's actually better to not have an entry object at all because it's a wrapper object that's a pure cost. It's better to just put the keys and the values right into the backing array. And that's what we do with Unified Map. It has a double-sized array, and the keys and the values go right in alternating. In the case of collisions, the key is replaced with a sentinel that indicates there's collisions at this slot, and the value is replaced with an array that's of a similar shape. It has key value alternating in it. So on average, but just by avoiding that wrapper object, the entry, it takes half the memory on average. But you have to watch out for this one method, entry set. It's not, it's a leak abstraction. If you really are backed by a table of entries, that's a constant time operation. But if you're not, you have to create them on demand. So for JS collections, the one downside is entry set is linear. But of course, we have all these iteration patterns that we provide. So we have for each key value. Just use that instead, and there's no garbage being created, like a whole entry set. Now, moving on to sets, the shape is similar, but now the memory usage is 4 times instead of 2 times on average. So why is hash set so inefficient? Well, a hash set is backed by a hash map. So everything I said about entries still applies. And in each entry, the key is used, and the value is just ignored. So factoring in both, each factor contributes double the memory, a total of 4 times the memory usage. This really hurts performance. If you iterate through the whole thing, the overall memory size matters, not just for the heap size, but for speed as well, for memory bandwidth. And then I alluded to this earlier, but we build other containers on top of these, so we don't want to be building on a deficient hash set and a hash map. So our multi-map, bimap, and bag are all built on our replacements for hash set and hash map. This is just a diagram showing how wrapper objects are so costly. It's not just because they have the references, but they have a header each time. And the header varies depending on if you're using compressed oops or 64-bit or whatever. The last point is about primitive collections. This chart is not totally apples to apples with the previous ones, because now I'm comparing an array list of wrapper integers with a primitive int list. We have primitive int lists, and Trove has a primitive int list, which I'm showing here as well. In this case, the wrapper objects wouldn't even exist if you didn't have the collection. So in this case, it is fair to count the wrappers as part of the collection. But you know, it's not totally fair. You would try to avoid autoboxing where possible. But the reason it's relevant is because of the thing we discussed before, where in Java 8 we have primitive streams, but it did not add primitive collections. So let's say you stack a few operations. You call stream, you do like a map to int or something, so now you've got back a primitive stream. Now you're dealing with integers, and you can do things like, you can do math on them. But if you need to store it, you're not going to want to store a primitive stream in a field on an object. The reason is that streams behave just like iterators. They're one shot. You can iterate through them, and once they're done, they're done. Has, you know, like with an iterator, has next would return false, and next would just throw. They're similar. They would just throw if you try to iterate through them again. So they're not appropriate to store in a field. If you really want to cache them and store them in a field, you have two choices. One, you could just collect them back into a collection. There is a box collector that helps you do that. But that's not great. Now you've got the memory of the previous slide. You know, a huge collection containing wrapper objects. Your other alternative, which I think is probably the more likely choice, is you just terminate it in a primitive array. You know, the same arrays we've always had. And that has perfect memory usage, of course. The downside, though, is now you've lost all the information about the type system. You don't know if that array has duplicates in it or not. You don't know if the order is meaningful. You don't know if it came from a list or a set. So I think it's important to actually have these primitive collections so that you can retain the type information, like whether it's a list or a set, without paying more memory than the array that it started with. Any questions on memory? Okay, last section.
One question. You mentioned the probe used linear probing for
Yes.
collisions. How come would you consider that for yours? Or-
Yes, and there's this whole like renewed interest. These are old topics, but there's a whole renewed interest I've seen this year in primitive collections, where fast utils got like rewritten in its internals, and cold bulky is a new one that is doing well on some performance tests. And so we kind of like are revisiting old assumptions too. And one of my colleagues is going to present on it at QCon actually. But the interesting thing is that probing seems like it would be bad because it can lead to chains of, like groups of collisions in the array, like a whole segment that's all collisions, and the collisions can interfere with each other. But the plus side is that they have better cache locality. If you're just iterating through an array, the CPU is going to prefetch the next few things. So linear probing, especially linear probing as opposed to quadratic probing, seems bad, but then in terms of collisions, good in terms of cache locality, and there's a whole bunch of trade-offs. So this is a deep topic. We can talk about it more offline. But they both can be good. Any other questions on performance? Okay. Getting back to API, method references. Method references are awesome. We love them. Java is the only language that I know of that has a feature like this. Like a lot of, like almost every language is lambdas at this point, but I haven't really seen that many with the syntax devoted just to a method reference like this. And when we started playing, when Java 8 first came out, even before it came out, we were playing with preview builds. And to play around, we of course used our own training materials, the kata. And so we started replacing the anonymous inner classes that we were teaching people to use with the lambdas, and we were loving it. And then some of them we were able to replace with method references, and we were loving that even more. And it's hard to describe, but there's something about the method reference syntax that we liked more than the lambdas for the equivalent. So there's one exercise where we take a list of customers in the kata, and we just get their cities. So if it were Java, you would use map. For us, you use collect, which has a naming conflict, unfortunately. So in this case, we could have used a lambda that's like customer, arrow, customer get city, or this syntax. And we like this one better, although I can't explain why, it just feels. And then there were other patterns that we couldn't easily convert into a method reference. And we were asking ourselves why, and is it even possible? So the second example here is where we take a list of customers and we filter those that are from London. And you can't easily write this as a method reference because let's say you did the : lives in, then there's no opportunity to pass in a parameter, like London. And is it even possible to write it with a method reference? Like, you could cheat and you can do it this way. You can make a method, lives in London. But that's not abstract. I don't think anyone would write a method like that. You want lives in to take a city. So what was interesting is this reminded us of a problem that we've been dealing with back to Java 5 days. And actually, now I'm talking about Java 5, it's a short tangent. All of these examples are shown in Java 8, but JS Collections is actually compiled with source compatibility to 1.5. So that's kind of the brilliance of the new compiler. It takes new lambdas and compiles into old interfaces that have existed. So you could take JS Collections 1, and for the most part, the one name conflict, just use it with Java 8 lambdas. But yeah, we did, like the latest release of JS Collections, we didn't have to re-release it for Java 8. It just works. So we've been doing this stuff since, well, even before Java 5, but the current format that you're seeing kind of has been the same since Java 5. And we always dealt with this problem of memory usage on these stateless lambdas. And so for this example, where we wanted to take customers and collect their cities, we used to have to do an anonymous inner class to get the city, and it was stateless, but it actually lives on the heap. So we would want to not create it all the time. And this is the style that we would promote. Create a constant, because it's a function from customer to city that's a string. The convention would be put the function on the thing that it's from. So we'd have a constant on customer. It would be called to city, and you just cache it there. Static, constant. You're only creating one function. And then in the places where you use it, like this, it actually doesn't look that different than a method reference. And what we're finding is that all these places where we had constants like this are the places we can use method references. Well, similarly, we dealt with this problem in the past where the methods that can't be a method reference, use a method reference easily, were the ones where we couldn't save memory as easily. So here, customers from London, you call select, you pass in a new predicate, this is the anonymous inner class syntax that we always used to use. And in this case, I have London as a constant here, but you have to imagine that it's in a variable or something. This is the thing I'd be closing over. The thing I'd have to make final or implicitly final. That's the city there. So I have to create a new predicate each time I have a different city. And so that is creating garbage. And so we wanted to avoid that garbage. There were some places where we had tight loops where and an iteration pattern inside of it where the garbage creation really mattered. And so we created a second form of each of these methods. We call them the with methods because they're just like select with and collect with. And they just take our name for it is predicate 2, or function 2 instead of like by function. And all it does is take a second parameter, and it's a different shape now. In this case, lives in it's a constant now. It's predicate 2. And the reason we're able to make it a constant is because the second parameter passed in goes throughout and becomes the city here. And this is no longer something being closed over. It's, and then, yeah, it's specified each time. And when you call select with, it's different. You pass in a predicate 2 and the second thing you want to pass all the way through. So we've had this all along, and it's been sort of a trick that was really only used for memory optimization. But now we find ourselves using it all the time because it works with method references perfectly. It looks similar to the previous example, but the types are totally different. Select with takes 2 lives in, and this is a predicate 2 instead of a predicate. So this increases the number of places we can use method references, and we just like how it looks, and we want to use it in more places. Streams don't have a lot of methods that take 2 argument forms. When they do, it's usually for reduction or something like that. So I'd like to see more of this kind of API in streams in the future. All right. We're about out of time, so I'm going to wrap up with a framework comparison. I'm not going to go through every slide here, every box, but the important takeaway is that these features kind of multiply. I mentioned, like, we have multi-maps as one feature. They build on top of our sets and maps, which are optimized. Each of these will have, like, all these iteration patterns. You'll have choices of eager or lazy, and it explodes. That's why it's a huge collections library. But a lot of it, I believe, deserves to be in the core collections framework. And I'd like to see it in Java 10. I have this slide where I gathered together all the links where you could go for more information. You could, of course, reach out to us directly, and I'll put our Twitter handles up top. We answer questions in Stack Overflow, just tag it with JS collections and we look for that. We've got our library and the training materials on GitHub, as Chandra mentioned, and our wiki there, links to all of our presentations, including the InfoQ one, but we have a whole bunch more on memory and performance, which is my favorite topic. We also have our engineering site where we talk about JS collections and other interesting engineering problems that we solve. All right, so with that, I just want to open it up if there's any questions.
What is fastlist?
Why is it called fastlist? Well, I think you named it.
My old joke is that it's faster to type than an array list because it saves one character. But more seriously, we've pretty much, as Greg was talking about, tried to, anywhere we see like a pattern and there's an opportunity to reduce memory usage or optimize, we have. So if you look in fastlist, you'll actually, and if you compare it with array list, you look at things like, very basic things like equals or hash codes. And you look at how it's implemented in an array list, and it will actually inherit its behavior from abstract lists, right? With fastlist, it'll be implemented directly iterating over the fastlist array as opposed to using two list iterators or using an iterator to actually calculate the hash code. So we tend to have, in the history of JS collections, we tend to have this focus on, I would say, memory first. Anywhere we can save memory, we do. That usually has a knock-on effect on performance. Beyond that, obviously, we care a lot about API. We want to have a rich API, so that's what we've tried to build. But those three kind of things going together, and sometimes they're at odds with each other, and you see like that being at odds can usually result in a lot of code having to be written. And we have a saying on our team, we say rock hard or go home. And so you got a problem to solve, like sit down and solve it. You can punt it, but then some developer has to scratch their head and figure out like how do I solve this problem, and it usually gets harder for them.
And since you asked about the name fastlist, like people are probably wondering, is there fastset and fastmap? And the answer is yes, there were. They were based on the same strategy that Raab uses. And so eventually when we dove deeper into performance and rewrote those, we had to come up with a different name. So those are unified set and unified map. The name comes from the fact that it unifies the best parts of Hashmap, which is a strategy for chaining collisions, and the best parts of Raab, which is the no-entry objects.
So the downside was when we open sourced, we have a large number of code bases that use JS collections inside of the firm, and renaming things is not usually greeted with a lot of friendliness from developers. So the names that we came up with long ago have stuck. So
the names of the concrete collections aren't that important though, because people tend to use the collections factories. So you're like lists dot and then mutable dot with. All right, there's another question.
Yes, I guess. You've got some synchronization collections with queries and so on. Do you have these formats?
I knew the first part, sorry.
Synchronized.
Okay.
Synchronized?
Yes.
Yes, so almost every mutable collection has a method as synchronized. For a synchronized wrapper, has a modifiable for an unmodifiable wrapper, and they all have two immutable across the board to convert to in linear time to an immutable collection.
And for example, if there's something like style.
Yeah, so we rewrote concurrent Hashmap as well. Is that your question? Yeah.
Not just synchronized map, but also
Yes. So we have a whole bunch of stuff. There's always something we won't have though, because there's so much out there. Like we look at other libraries and try to take bits that are useful and implement them in a style that matches what's there in JS collections. So I feel like the functionality like the thing that's out there that's most similar is probably Scala's collections framework, with the caveat that there's things we can't do because we don't have implicits. But that's the one that feels like the most complete API, although they don't have multi-mouse in the back. So yes.
Well, I think it's more a comment, but it seems like a lot of the problems with string API were kind of like apples and oranges, because string API isn't trying to be a collection of framework. It's it's more of a unbounded sets. It's, you know, it's not trying to replace a lot of the old Java collections. Maybe Huawei is a but even for the query language, you know, a string is not, it's a readable, you can't go back, like you mentioned. It is really about something that's being consumed rather than a collection framework, where you might be doing more set data, the usual set operations. I've seen, actually, my question though is that I've seen query DSL, which does a lot of what you do in query DSL.com, and also Java object-oriented queries. Have you compared yourself with some of those frameworks?
I'm not familiar with the first one. I have seen the second one. There's a lot of competition, and there's so many pros and cons. A lot of the ones that have cooler syntaxes will use reflection or proxies or something. So, you know, we always, going back to the first versions, we've always emphasized performance first. And like that's why Java 8 is such a big deal to us, because the syntax was anonymous interclasses and it was like horrible syntax until Java 8. So now it's like we're taking these old Java 5 libraries and they look awesome now in Java 8. So yeah, when it comes to trade-offs, it's been performance first, like Don talked about, and we're excited about the APIs. So what's it called? JOOQ. Yeah, that one I think is a cool API. Not sure about its performance, but I didn't even include it in our performance test. I don't think it performs that well. But yeah, like I could do this collections framework versus that all day. I won't do that. But there's just no, they all have their own trade-offs. Yes?
So do you have any app that was maybe internally developed there which used collections and you had a chance to sort of benchmark the 99th percentile using regular Java collections versus GS collections? Any like low latency situation?
We have a lot of micro benchmarks which we've open sourced using JMH, which we love. I don't have a case study like you're talking about of an entire app that was all using either streams or just Java 5 style collections and converting the whole thing. Because it's actually very easy to take a code base and replace all of its sets and maps. But it's a lot harder to replace the iteration patterns with things that are higher level. So just replacing the sets and maps, like doing it across the whole code base, most sets and maps don't contribute to the overall performance, but a few do. And we have seen significant, usually memory benefits, especially large caches, like 100 gigabyte caches that have a set of everything, for example. That'll make a big difference in terms of memory usage. And some of the ones in a hotspot will matter for performance as well, for like that input. But I don't have concrete numbers. It varies for that anyway. Yes?
So first question is, does it have any dependency on any third-party open source libraries or anything like that?
No. That was important to us. No dependencies on third parties.
So in case of Java 9, they are refactoring the Java 9 into like jigsaws and they can pick and choose whatever you want. Do you have any plans to do something like that, so that if I just want to use your set-related functionality, then I can just strip out and get a minified version of the library?
It's a really interesting question about modularity. We're going to have to, like, we're paying attention to what's coming in Java 9 and beyond. I'm not sure what the module system will look like yet, but if it's something we can use, I'd be happy to. It would be great to modularize JS collections even further. It is already in a few modules, but the main collections jar is big because it includes all the generated primitive collections.
One of the biggest challenges we've encountered recently, which we're not going to see the benefit of modularization on, is on Android. Right? We have a very large collections framework, and it kind of barfs when you try and run it on Android because only the ability to, I guess, have 64K methods. We have a lot of methods.
But that's where my question came from.
Yeah, the thing is that Java 9 features won't necessarily benefit Android at all. So I don't know what to do. Like, it's a lot of effort on our part to upgrade and use cool new features in Java 8 and 9. It's also a lot of effort to modularize without doing that. We probably don't have the bandwidth to do both. So I'm very curious what Jigsaw will look like, and I will be paying attention, but I don't have any concrete plans. Yes?
Is there any of the library which works with the collection which is dynamic? For example, let's say I have a group by, but what if a new elements being added on the underlying collection? Will the results modified, or do I need to code it again or create a new stream? And
I think like a library might be.
yeah, like let's say I have a 10 items, I have a group by. So I have a group by results.
Oh, so you modify the
yeah.
container, you want to modify the multi-map afterwards?
Yeah.
No.
Like
yeah.
Like a stream, or like as rows gets added on the underlying collection, I have a the summary view.
Yeah, I understand. No, the short answer is no. We're focused on in-memory collections. People have asked, well, a question that I thought was strange at first, but I'm getting used to it, which is like how we compare it to RX Java. And at first I thought it was like, no, that's totally different. But actually the API looks kind of similar in some ways. Like they have filtering of a bunch of things, and they have transforming a bunch of things, and that's like our select and collect. But RX Java is tailored to a case where you don't have the whole thing in memory. It's a stream of events, one at a time. And ours is tailored towards you do have everything in memory. So they're both useful in different cases.
So I'm curious about some of the organizational issues. How do you is this all maintained by a core team? Are there multiple groups that are kind of contributing to it? And then just the decision to open source this, and I work for a big bank myself now. They're known for being a little cagey about their IP. Just curious about how that all played out.
Yeah, open sourcing from a bank. It's a question I get frequently. There's a lot that went into it, so it's a big answer. Maybe we can talk about it offline. But there is a platforms team that we are on. JS Collections is not our full-time job. We kind of add features as we see the use case in some other app. But that's been for a long time, so it's grown a lot. And then open sourcing it took a while. There's probably more hurdles at a bank than elsewhere. There's more that I think will open source in the future, but I have no idea when. And I could say a lot more, but it'll take all day, so let's talk offline.
Any corporation, it's a problem for any corporation, but for bank and especially like Goldman Sachs, probably with some special arrangement.
Yeah, so thank you, Don. You did
Share some thoughts if you want. Sure. We are a bank, and we're not just for not-for-profit. So there were really good reasons, I would say, like for us to open source JS Collections. Part of it was myself and Vlad Zakharov, who's taking a picture of me right now. We were both on the JSR 335 expert group, which got lambdas into the Java language. So I've been waiting for lambdas in Java since 1997. So I'm patient, and we're here now. But we view Java as so important to our organization, and it's interesting if you look at the JSR 335 expert group, you get members like Brian Getz was the lead, you have Josh Block, you have Kevin Brilliant, who's the head of Google Guava, folks like Doug Lee, and various other industry luminaries, and then you have like me and Vlad going, hey, we're going to tell you how to do lambdas. What do you think? So. Part of, for us, like open sourcing JS Collections, it was very important for us to actually engage with the community, right? To share what we thought were important changes to the language that hopefully, I'm assuming you're in a Java user group meeting, we all love Java. It was important for us to see that the language evolved, and having our source code out there. Yes, it's hard to get something open sourced in any corporation, let alone a bank, but we see like the value of engaging with the community and being able to kind of meetups like this actually talk about what we've done, what we think potentially needs to be done. We can actually share that openly, right? So.
Oh, it makes sense. It's just convincing the people that can say no that it makes sense.
I'm a Taurus, patient, and sometimes bull-headed. I'm taking questions now. Look at that.
Has anyone ever thought about using this approach for SQL?
I think, people have done that, right? So I guess you can link, right? This one example.
So link,
yeah. that's definitely not something we're going to be taking on with GS collections.
What is the question?
If somebody's thought of taking the same approach with something like SQL. So, one or the other.
You haven't spoken anything about the garbage collection?
How it happens or when it happens?
Yeah, I mean, is it efficient in terms of garbage collection?
I want to say something like, from like, dude, where's my car? It's like garbage collection is both mysterious and powerful or something like that. Power is only exceeded by its mystery. Yeah, so we pay as much attention to, I guess, garbage collection as we can. First, we try not to create any garbage if we don't have to. I'll give you a good example. Look at add all in array list, and what you'll see is the first thing it does is it does toArray on the incoming collection. We'll go so far as to check to see if I'm adding a fast list to a fast list. Hey, fast list is my friend. I can reach in and get his array directly. I don't have to make a copy of it, right? So that's very garbage collection friendly because I'm not creating any garbage. In terms of measuring garbage collection, it's not something that we go out of our way to measure. Once again, we go out of our way to try not to create it. And some of the things Craig was showing with all of our with methods. We had this nice term for what we used to call fat-free closures, where basically we don't want to have to create an instance of an anonymous in our class, so we'll hoist up that into a static method. And once again, now with method references, we don't have to do that. That's done for us. But yeah, nothing. I don't think we've actually ever sat down and tried to measure garbage collection. We tend to measure performance, but not garbage collection.
Right. So our GMH tests that I mentioned before, they cover everything because they iterate for a while. So if garbage was a problem, they would be slow. But it's not something we test for separately.
I just want to say it's really refreshing to hear. I've always been a fan of high performance stuff and minimizing garbage and all that. And I've been endlessly frustrated by seeing the code coming out of Sun and now Oracle, where their attitude has always been to let the garbage fall where it may and somebody will come along and pick it up. It's just a silly approach to coding. When you can avoid making garbage, you're much better off doing it, and everything works more smoothly. So congrats, you got it.
Thank you. We got a blue bin and a black bin. There's recyclable.
Yeah, exactly.
Save the planet.
Yeah.
So even today, I could see with the smaller APIs of the regular Java collections, people struggle learning it and doing it correctly. With this expanded huge set of APIs that with the GS collection, how do you see it?
It's definitely, it's more to learn, right? And for us, this was why we actually have two katas now. We have the original kata and we have now what's called a mini kata, which you can actually, we haven't open sourced the mini kata yet. The regular kata, we teach it in an 8-hour class. It can be accomplished on your own if you're really, really aggressive and focused on it. I've done it in like 2.5 hours, which means you can probably do it in 2, because I'm slow. The mini kata is meant to take like 2 hours. You can actually see the mini kata though today. I have 2 InfoQ articles I wrote. They're called GS Collections by Example. The mini kata is actually in the second article. And it's hard when you're right on that. You have a very large API. It's hard to teach that to people, right? And there's no magic wand I can wave, right? Although what I can tell you is that once you start to learn some of the concepts that we have, things start to just make sense, right? You understand that there are different things that we have, like we have mutability and immutability. And that, there's some parent of that which we call a readable interface. And once you understand that there's kind of this triad of interfaces, that results in an explosion of things that you can potentially learn, but you'll start to think about like, well, I've got some collection type, let's say list set, bag, or map, and I can either be mutable or immutable or readable, right? And while you've got this multiplication of total concepts that you can memorize, the smaller group of concepts actually helps you to start to navigate it once you understand the way it looks. The API at the top of the hierarchy, there's a lot of it. Our thought is like the IDE helps you, so please code in your favorite IDE like Eclipse or IntelliJ or NetBeans and use the dot and control space, and we're going to help you find what you're looking for. In our case, the list may be longer, but it's probably there. You're not going to have to go somewhere else to go find it, and that's what Craig was talking about with collectors, right? Once you hit collect, I did dot collect, and control space doesn't help me anymore. I have to control N to collectors or type collectors and then dot, right? I have to know that it exists. So we also look at the way that, because we have so many concepts, we've been very careful about how we group them. Our thought was, and you can all be my experiment then if you like, take a look at the way the concepts are grouped in the IDE. Don't look at the Java doc because the Java doc doesn't group it very well. It's like one big flat list, right? Too much. But we've grouped it by type, and you'll see like within packages, as you expand them in your IDE, you'll see like all the concepts for that type. So for list, which would, so say be a root package, it had maybe mutable list, list iterable, and immutable list. And actually there will be another one called fixed size list, which we didn't talk about tonight. But our thought was like group these things together so you can actually navigate them in the package hierarchy. And we try to use packages to help kind of break down this large mass of stuff, the 1.2 million lines of code into something that you can actually digest and navigate through. But it's hard. Our thought is like, we teach katas, hopefully this helps people do it. We can, we can do a much better job in our Java doc. So apologies if you go there. If you see there anything that's missing, please complain about it, file a bug request and say, please document this stuff, and we'll do that. Just something we're looking to do, and really this is kind of our next step in evolution for JS collections. We want to open it up to the community to contribute to. So right today, we do all the contributions internally. We have a core team, as Craig was saying, that actually maintains the framework, but we're not the ones that are typically contributing to it anymore. They're actually folks, we have like 3,000 to 4,000 Java developers in Goldman Sachs, so it's not 9 million, but there's quite a large number of use cases that get encountered by leveraging the library, and what we have is a lot of internal contributors. I think it's somewhere between the order of maybe like 25 to 50 developers that have been contributing to JS collections internally. And before that, in the older library that we had internally, there was probably another 25 to 50 over the years that have contributed to it.
So with respect to this contributing of developers contributing towards it, this is like a certain set of project that people contribute, or it's like everywhere? And is there any, is it backed up by any kind of rewards to those developers, or?
I'm sorry, you're going to have to repeat that.
Right, so you have a lot of developers that are contributing towards your
Yes.
GS library. Now, are these developers within only?
They're all GS.
They are, no, but they are in a certain set of projects, or they are just all over the GS?
We have people in Salt Lake City, in Tokyo, in Bangalore, in London,
What is that general motivation for contributing towards it?
So you need it, you build it.
Yeah.
The motivation is the same for anything open source. Usually it's people who already use it, who want something, or just want to get their hands dirty and get involved. And usually, they'll start with optimize this or that, or increase coverage here or there. It's a good way to learn.
So if someone is adding some feature, how do you manage the quality of the feature that's being added?
I reviewed it, and it's painful.
He reviewed my code. It never gets committed the first time, or the second time. Maybe the fifth time, I'm lucky. Yes?
Any plans to make it distributable JS collection on a cluster?
No.
It sounds like a lot of fun, but once again.
All these things like SQL, streaming, and distributed, it's just a different framework than what we have. Ours are just in-memory one name.
It's available in one jar file?
There's an API jar and then there's an implementation jar.
But if you're using Maven or Gradle, you just import JS collections.
And it'll take the dependencies.
And the dependency set is mentioned on GitHub, so no reference.
Anything else? Well, thank you.